classical particle system. Benjamin, floor is yours.
Yeah, okay, thank you very much. So yes, pleasure to give this talk here. So I'm going to talk about GHG. So there's been a lot of talks about box-ball systems and a lot of discussion also about GHG already. So I'm going to be repeating a little bit of the things that have been said, but I want to kind of give an overview of the general ideas to show how general they are, and also some little kind of more recent results. So there will not be a lot of new results, but some recent results about deriving GHG. So the first thing is that the idea here is to look at emergent dynamics for complex systems, right? So you imagine a system of many particles in interaction, or any other type of microscopic dynamics, which is complicated to describe. Now I know in this audience, that's what we want to describe because it's integrability, so we want to describe the whole thing. But I'm saying here, well, maybe it's still complicated when you have a very large system and you want to see what happens at large scales. Okay? And the general idea is that at large scale, there should be new laws that emerge, and hydrodynamics is such a type of new laws. Now, there are many types of dynamical systems we can consider. The basic thing is particles in interaction. And in previous talks, there was some discussion of that. They can, they could be stochastic or deterministic. And at large scales, where there should be something new that emerged, for instance, sound propagation, water waves, this is large-scale phenomena, right? Just a wave propagating on water is, 10 to the 26 atoms, molecules of water that interact with each other and give some new emergent structure. Water waves themselves can be considered as a dynamical system. KdV equation is an emergent equation, and itself can be considered as a dynamical system. It has solidity, it has structure. And this dynamical system can itself have new emergent laws. And people have been studying gases of KdV, solitons, for instance. Okay, so there's all kind of structures of emergent laws, and this is an interesting thing to ask. Okay, so relevant to this workshop, of course, you don't have to have just particles interaction. You can have all kind of things, for instance, serial automata and box-ball systems. So there's this general question of emergence, which I think is very interesting. And in fact, this is, I think, some of the most interesting problems of mathematical physics of actually proving emergent laws for microscopic systems. Okay, and so for GHG, BBS, and hard rods apparently are the only two models where we can actually prove things. Okay, so now, so what is the problem is the large-scale statistics and dynamics. So there are two important things. So one thing is the thermodynamics. So we look at states, that's statistical ensembles. So we've seen now already in many talks. Our initial state is not a fixed state, but is a random distribution of many configurations with some measure. For instance, Gibbs measure, that's the most standard thing, right? That's century or more old. It can be classical or quantum, and here the way I write it is some set of particles, X and P is some set of n particles if you wish with interaction. But one question is, what are the relevant statistical ensembles to study? There's all kind of measure one can write, many. What are the relevant ones? This is a crucial question. The other thing is, well, this is just the initial state. Now, how do things evolve in time? Okay, so you can imagine that you have some initial measure, and then you look at some observables that depends on all these, the values of the positions and momenta later in time t from the initial measure. So at later time, there's an induced, time evolution on the measure itself. And you ask about, what happens at later time. So quantum and classical can be asked. In fact, any dynamical system, right? It doesn't need to be Hamiltonian or anything like that. So the idea here is that at large enough scales is hydrodynamic theory that should describe what happens at, at large space and time, large enough scale in some way. To give an example, these are examples that were already discussed. This is the Riemann problem we discussed this morning. Here is a setting up of the Riemann problem for the hard rod gas. We've seen the hard rod gas. Okay? So it's a gas of rods that just interact by elastic collisions, exchanging the momenta. Okay? And so this gas of rod here is the homogeneous version. You can do the inhomogeneous version. Now we know how to do it. Here I can set it up, for instance, by taking different distributions on the left and on the right. And here is a specific example, right? So you have an initial measure. The only constraint on the xdp is that the x's should not be closer than a certain distance r as the length of the rods. Okay? And then you weigh the configurations on the left by putting some function of the momenta. The momenta are conserved on the scattering, so okay, that's a good thing to do. but you weigh that differently on the left and on the right. So this is explicit measure. You can do that, you can do different things, many different things. And then you ask a question about what is, for instance, the average number of particles, the density of particles at position x later on in time. And that's this A of xt, that's my observable at xt. It's just this delta function, right? And it's well defined, probably you can put that in computer calculator. In fact, that you can calculate that quite explicitly, and we have explicit results for that from GHD. There were some results in the box-bowl system this morning. So one has results even, also for this problem. And this is a typical question that you can access using hydrodynamics. Okay? You can also set up, so this is little pictures is numerics compared to the analytic formula from GHD, which looks like it works well. Okay? So you can also set up this Riemann problem in a box-bowl system like was done in the morning. So the way I write it, you just sum over all configurations with different measures for the sub-configurations on the left and the sub-configuration on the right. Okay, well, these different measures are, of course, this is just one measure for the whole configuration, but of course you can decide to, on the left, put a certain temperature, weigh the different solutons in a certain way, on the right in a different way. And then you ask what happened at large time for some local observables. What is local observables in the box-bowl system? Well, for instance, you can look at a function of the time-evolved configuration. So you know how to time-evolve the configuration in box-bowl, and look at the sub-configuration of this time-evolved configuration around a certain point x, x plus or minus epsilon. Okay? That's the local observable in box-bowl system. Okay, so we can can look at any function of this, number of bowls or any whatever function you want. And again, so hydrodynamics will give you information about that. Okay. Now, what's the relation between the set of states I talked about the thermodynamics and hydrodynamics? Well, there's a crucial relation, which is that the way that you get hydrodynamics is via the hydrodynamic assumption. Okay? And that's the thing that is difficult to prove. And in all the proofs of hydrodynamic equations, at least in the integrable context that we have seen, this assumption is not proven. This is not the way that it is done. It's difficult. It's different ways that you get the hydrodynamic equation. Okay? But the principle is that. So what's the principle? Is that you divide your system, many body system, into microscopic, mesoscopic, and macroscopic, if you wish. Microscopic is there on the right, is just the particles move around. Okay, it's complicated. Mesoscopic is a fluid cell. So it's some space-time region that is large enough compared to the microscopics, but small compared to the macroscopic. What's the macroscopic? Well, small compared to the length scale over which things change. What things? Average of local observables. The length scale over average over which things change. And the idea, so you separate in this scale, and then you pose it, or you conjecture, let's say, that in these mesoscopic cells, the system has time to relax. There's a lot of interaction, the system relaxes. Okay. Relaxes to what? Well, to the physically relevant thermodynamic states. So this is the idea. So here, that's kind of a crucial equation of hydrodynamics, right? The average of any local observable, local, so supported on few sites in the box-bowl system, on small regions and hardwoods, at time t, let's say large enough time, large enough x, something like that, in the initial state is approximately equal to the average of that same observable in some stationary homogeneous state that represents the fluid cell. Okay? What's this stationary homogeneous state? Well, here I write it in the Gibbs form, right? Exponential minus beta I, qi are conserved quantities, right? So there is some set of states parameterized by some parameters, and these parameters can depend on where you look at in space-time, where you look at with your local observables. But it's that set of state. Okay? So this is the hydrodynamic approximation, at least for the earlier scale hydrodynamics. Okay? So it's a very rough approximation. Once you have that, you can go quite far. Now I want to discuss these states, these Gibbs states. What are they? Actually, this is crucial and rather deep question. Relaxation. Where does this many body system relax? Well, the naive thing is to just take the Gibbs form, right? So you say the states are of the form exponential minus betas, some generalized temperatures, times q's, some conserved quantity. Okay. Now, usually people say, and it's correct, that these conserved quantities are not any conserved quantity. They should have specific property for this to represent relaxation. And they should be extensive. That's the property that is being usually mentioned. What does it mean extensive? Well, that's a bit tricky, actually. But naively, I can write it like that. I can say, well, if Q is extensive, it can be written as an integral over X, or a sum over positions, of some local observable, local enough, supported on a few sides, something like that. So some local observable, which is itself, of course, a conserved density, and that will generate a continuity equation. Okay, so that's the idea. This is very hand-wavy. It's not very precise. Maybe I come with something a bit more precise. In different contexts, this concept of extensivity can be made mathematically precise. So for now, we keep it like that. Okay? For instance, in the hard-rod models, actually, it's not too difficult to construct local observables that are conserved densities. This type of thing is conserved while the momenta are conserved, and you look around the position X, you take the density of momentum there. And if I integrate over X, that thing, integrate over X, I get the total charge, well, the total density of momentum around momentum P. This is conserved because set of momentum is preserved under the hard-rod evolution. So that's a good conserved quantity. In fact, it's a one-parameter continuous family of conserved quantities, right? So instead of a discrete index here, I have a continuous index, and I can think about the function W of P, and that's the type of weight that I can put, and that's what I had in my example of the Riemann problem, right? I had different weights on the left and on the right. Okay, so these are my generalized Gibbs ensemble for the hard-rod gas. It is a bit naive. One has to ask the question, what kind of function W of P you should put there? And typically, the function should be such that, well, the average of local observables you calculate should exist, right? Perhaps a bit more conditions, right? So, I mean, function should grow at large momentum or something like that, okay? So, but this is, naively, we take that, and that should be our Gibbs ensemble. For the box-ball system, we've seen actually already. And here is very nice because people have done a lot of nice work already, and there's a way of identifying in the box-ball configuration where the solitons are, following the solitons, right? A bit like for the hard-rod, I can identify where the momentum P is now. Okay, so I identify where the soliton is. I take the function that says is the soliton there or not. That's my density. And the Qi, the total and sum over X, is the number of solitons of length I or velocity I. And this is conserved on the dynamics, the box-ball dynamics. That's perfectly good ensemble, and that's the one that was used in some of the talks this morning. Yes, okay. Now, this is nice, but it's a bit nice. So why are these the right state? That's Bozeman told us maybe it's not sufficient. Well, it's not completely clear, but there are some principles which I think, or we think, or many people think, are the right principles for the right states under relaxation. Right? So you have a dynamical system. You want to know whether it's relaxed to. What are the states locally that you have to use for your hydrodynamics? So the basic idea is that you look at the state. A state is what, well, in classical system is a measure on configuration. You can think of that as some positive linear map on set of observables. In fact, in the quantum chain context, is a very powerful way of thinking where you have an algebra of observables and look at positive linear map on this algebra. Okay, so you have some map on observables that give you their averages. Just that. Now, these maps should satisfy certain conditions. This should, okay, the dynamics gives rise to some evolution of the observable, right? Like we've seen. For box-ball system, this can be seen explicitly for hard-rod as well. And the two main properties that we ask for this space is the following. First of all, it should be space-time stationary. Of course, we think about local relaxation, so it goes, locally. Your system will go to something that is almost stationary. It moves slowly in time, but almost. But second thing, so this is not sufficient. There are many, many, many states that are space-time stationary. There are actually too many of them. It's a very, very huge space, and it's not the right space for. It's too big for relaxation. The other condition is some kind of ergodicity. In fact, perhaps something stronger is necessary. Some clustering in space. So if you look at the local observables here in X, kind of far, and some other observable as 0, well, they should not be correlated too much, right? And that's, if your system relaxes, it forgets about information. And the idea is that, yeah, so, things at large distances should not be correlated too much in some locally interacting system, okay? So these are two conditions. And the question is, what is this manifold? It has some manifold structure, potentially infinite dimensional manifold structure of states, and the conjecture is that this is the right manifold of states for local relaxation. Right? So you have some set of states, and Hydro tells you that everywhere in space-time, your system, from the point of view of local observables, goes to some point in this manifold of state, everywhere in space-time. So you have, a bundle or something, space-time, and on top of that, some manifold. Okay. So, so this is the idea, and the question is, what is this set of states? Well, the conjecture is that indeed the Gibbs form is, in fact, the full set of states of that form. Okay. And then there was one thing I told you, that the Qs should be extensive, and I told you that the states should be clustering. So the extensivity of the conserved charges there and the clustering of the state are connected to each other. In fact, perhaps this is the correct definition of an extensive charge. Is a charge such that if you put it, a quantity that's conserved in time, so that if you put it in an exponential to define a measure, then the resulting measure is clustering. Okay, so clustering, perhaps strongly enough clustering, that, these are details, one has to work out the details. Okay, so that's kind of why, the Gibbs states are clustering, should be clustering, and that's why, these should be the right state for relaxation, because, so this is kind of general principle. Now, why this manifold state is actually the right one, but it satisfies a number of interesting relations. In particular, there is this almost everywhere ergodicity. So if you integrate or sum over time, and if you average over time a local observable, you would expect that this time average is equal to the ensemble average. Okay? Now, this is hard to prove, but one conjecture is that in this set of states that are space-time stationary and clustering, this is true at least almost everywhere. So in fact, in quantum spin chains, a lot of that can be worked out quite explicitly. In particular, in quantum spin chain, this large volume limit of Gibbs state with finite range conserved quantities exists, gives rise to space-time stationary states, and is clustering. So it satisfies all the right property in quantum chain. This is kind of rigorously proven. This relation holds, so there is ergodicity. And more than that, there is the linearized Euler equations and hydro projections all work for all these states. So there's a lot of strong results for all such states that are clustering. So anyway, so this is the manifold of state that we look at, and supposedly the Gibbs form is actually the correct set of states. Now, so if you want to prove things rigorously, like in box-Ball system and all that, what I'd like to see is, prove what is this manifold of states. And okay, so this is the set of states, and now that we have the set of states, well, we do the hydrodynamics. Okay, so this is a kind of general idea, right? You can do that for any dynamical system, locally interacting. So what do? We do this hydrodynamic approximation. So we do that, we just assume this is true and nothing else, right? Or maybe we can prove it, that's a bit better, but hard to prove in general, okay? And once we assume that, well, it's not too difficult to get in an actual dynamics for this set, these points on the manifold, or this set of GGEs, these xt-dependent GGEs. How do we get the dynamics? Simply by writing the conservation laws, dtqi plus dxgi equals 0, where we know that the conserved quantities, well, they are conserved, and they are local, so there's some local densities in there. And since this total quantity is conserved, its local density should satisfy a conservation law. One question is there always a current GI that such that QI satisfies the conservation law? And again, in quantum spin chain, that can be proven in quite some generality. Okay. So, okay, and once we write that, we just combine this conservation law with this approximation to write a conservation law for the approximated average densities and currents. In other words, you write dt qi plus dxi equals 0, where qi now is the average of the density in that state at beta xt, and gi is the average of the current in that state beta xt. That now becomes an equation for beta xt. So it's an equation for something that moves in the manifold of state, right? And or a moving GGs. And this is the Euler equation. So this is the universal Euler hydrodynamic equation. So whatever system you have, it doesn't matter what is its dynamics, how you write it, Hamiltonian or not, quantum or not. You do that, and you get a set of equations. And this is the hydrodynamic. So some comments on that. What does it actually mean, this approximation that I wrote? Well, okay, it's not, we've seen actually in some talks this morning, the hydrodynamic limit, also yesterday. One has to scale things in a certain way. So one way of writing is like that. You have some initial state, and you assume something on your initial state. if the assumption is not satisfied, maybe you wait a bit of time and then eventually satisfied, something like that. Okay. Whereas the assumption, we assume that this initial state varies on large scales. So there's some scale L over which all the averages in that initial state vary, x in x. Okay? They're quite constant, but then they vary a little bit on some scale L. You make this L large. So you have to look at families of states which are more slowly varying. Okay? And then you evaluate local observables at space-time point Lx, Lt. So you look very far in time, very far in space. And the conjecture, the thing to prove is that this converges to an average of this observable in some GGE, in some of one of these manifold states. That may depend on what is this xt, okay? And that these betas satisfy the universal Euler equation. So this is the meaning of Euler scaling limit and Euler equation in a general fashion. Okay? So in particular, there's no need for the system to be chaotic or anything like that for Euler scaling limit to be formulated. So if the system is if the system is chaotic, perhaps the set of states, the manifold of states is very small. And actually, I was writing something here. If probably one can maybe define, there was a question that talks about defining integrability. Define integrability, at least for the dynamics, by saying that the manifold of clustering space-time stationary states is infinite dimensional, or define non-integrability by saying that it is finite dimensional. That's what one expects, but there's no proof whatsoever, as far as I understand, of finite dimensionality of this manifold for chaotic model. It's easy to prove infinite dimensionality for integral. So you see, all the specificity of the model are within that manifold. The rest is completely general. Just write your Euler hydrodynamics. Okay. So this one can write this Euler hydrodynamics in the quasi-linear form. I said this is an equation for the betas, but so the betas, like the coordinates in the manifold, are the dynamical variable. But it doesn't need. We don't need to take the betas, the temperature, as dynamical variable. We can take the conserved densities instead. In principle, there's a bijective map between the average conserved densities and the betas, at least for some regions of betas. That's model dependent. Okay, so if you change to the Q, then you get the so-called quasi-linear form of the hydrodynamic equation, which involves the so-called flux Jacobian, which is the derivative of the currents with respect to the densities. That's the crucial object in hydrodynamics. It has a lot of information. In particular, it has real eigenvalues, which correspond to, real eigenvalues, okay, it doesn't want to show it, real eigenvalues, which corresponds to the fluid velocities. So the sound velocities in an actual system are just the eigenvalues of this matrix. And you can ask about the sound velocities for any dynamical system. And so that will describe what happens if you perturb the system a little bit and waves come out. So the eigenvalues of this matrix tell you at what velocity they come out. Yeah? Okay. In particular, the effective velocities of GHD are the eigenvalues of this matrix. Okay, so and satisfy other properties. Now, so let us work this out for integrable system and get the GHD equation. We've seen them already. Okay, so let me do it for the hydrodynamics. That's interesting because yesterday we saw so Chiara derived the equation, hydrodynamic equation, in a very different way from that. It was a rigorous derivation. It's not rigorous. This is based on general principles, and you get the same equation, but the way is very different. Here, there's no contraction to free particles or anything like that. It's just hydrodynamics. Okay, it is less rigorous, but perhaps kind of more powerful in the way that, in the sense that you can go very far with that. But in any case, how would I do that with the hydrodynamic ideas? I would say, okay, I look at my conserved densities in the hard rods. Remember that the conserved densities now are parameterized by this one parameter family, the momenta. I denoted theta here instead of p for some reason, and then I call this average conserved density in the GGE. I call this rho p. This sub p there is for particle or quasi-particle. For some reason, it comes from TBA thing notation. Anyway, so rho p of theta, which is just the average of this conserved density within the GGE. Now, I would like, in principle, to evaluate it, and here's how one would have to evaluate it, right? You have to sum over the phase space, integrate over the phase space of your hard rods. And here I forgot the condition that the rods should not intersect. Of course, the x's are constrained. put the right weights on the momenta, and then impose, of course, that they are on a finite volume L, from minus L over 2 to L over 2. So I impose all the rods are there. Perhaps some over all possible number of rods, can put more and more and more. And then with 1 over n factorial for the classical kind of distribution, and divide by ZL, take the limit L is large, and that's your average. But I don't need really to do that for QI, because instead of this is the map from the betas to the QI. That tells me how to map the temperatures to the density. But I can take the Q thetas as variables that characterize the state instead of beta. So Q thetas are some numbers that characterize the state. But of course, eventually I do need to calculate something. I need to calculate the currents, and I would need to calculate all that stuff. Now, there's different ways of calculating currents, but we've seen the collision rate on that. And so let me just, go with the collision rate on that without having to do this big computation. Collision rate on that just tells me that, well, let me follow a quasi-particle, right? So here, one rod that has a given momentum and follow the momentum, not the rod. The rod goes around like that, but the momentum. Because that jumps around. And as it jumps, the kind of basic velocity gets modified by adding all these shifts, and that gives an effective velocity, right? So there's an easy formula for this effective velocity. You take the bare velocity and you add all the accumulated shifts, where the difference of effective velocity is the probability that there be a collision between a rod of momentum theta and one of momentum alpha, essentially. So, okay, so there's some easy argument, back of the envelope argument that gives you this equation. Where the phi, here is my notation for the scattering, the two-body scattering, is just minus r, because this is the length that is acquired every time there's a collision. Okay. So you get that, and then the basic idea is that the current for the conserved density theta is just effective velocity times the density itself. This is the idea, just multiplied by effective velocity. So this has to be shown. That was a question I asked you today in one of the talks, but I think it's not very hard to show that this is the case in a hard rod and also in a box bowl system. This is the right current. Okay. Once you have this right current, then you just write the conservation of the season currents and you get the GHG equation, right? You see, this is, you get the GHG equation from conservation law, the hydrodynamic conservation. Okay, this was proven some time ago already in different ways. It was explained by Chiara yesterday. Okay, but that's the way of getting it from hydro. You can do the same for BBS, where now phi is minus 2 minimum theta alpha. Okay, so this is the length acquired by soliton theta as it hits alpha. And in my convention, phi is, either if it hits on the right, then is the negative of the length that is acquired on the right. If the soliton hits on the left, the negative of the length that's acquired on the left. So it's kind of a good convention, so that you just have a minus 2 and that's it. Okay? And when you do that, then the effective velocity takes this form, and this is exactly the form of it. So that's very nice. Okay, so we have the GHG equation, but then the idea is that actually this goes much beyond these two models. Right? And doing these two models, one can do things specifically. It goes much beyond. So it, in principle, is something that is true for every many-body integrable systems, quantum or classical. And the basic idea is the factorized scattering idea. So you have some interacting gas or whatever, something, okay, into some system, and you let it evolve in time, forward or backward. Maybe it has a forward-backward evolution. Let it evolve in time, and see what happens. So time here goes downwards. See what happens. What comes out, right? So if you have a KVV, what comes out are solitons and kind of waves. If you have BBS, it's just solitons. If you have Toda particles, which are repulsive, it's just the particles. So stuff comes out. These are the objects, the asymptotic objects. They carry some quantum number, and even classical, some number like the momentum. Maybe there's some internal structure like a spin or something. So they carry some numbers. This is your asymptotic space. And in integrable systems, it turns out that the scattering, if you send a lot of these stuff together, they interact and then come out, you get the same momentum. Okay? More than that, the shifts or trajectories of these asymptotic objects is, satisfies the Yang-Baxter equation. So is the sum of the two-body shifts, the trajectory, as if the particles had interacted just two-body at a time, far apart in space. So that's the idea. So this is something, and now the point is that the hydrodynamic for integrable systems only needs the interaction of the two-body scattering. So the idea is that you can essentially follow this asymptotic object as it gets into this many body system, it's hard to see, but it's still there somewhere. It moves around a bit, and then it goes out, okay? And the way it moves is completely determined by this two-body scattering. This is true even in quantum system, where for your two-body scattering shift, you just take the derivative of the log, there's a log missing, of the two-body scattering phase, S is e to the I phi something, okay? So that's the idea, and then if you do that, you get that equation, and that equation turns out is valid for many, many, many systems. Now, I don't want you to recall that. This is just to show you that it's very general. For instance, you can take the KdV equation and put a lot of solitons. Actually, there was some discussion this morning about that, and that equation holds. The hadrons, the Toda, the quantum model, Lieb-Liniger, BBS, that equation holds, where you can evaluate any physical quantity, average, just using this rho. This rho, remember, characterizes the GGE. And these are examples. The KdV field is 4 integration theta, theta rho, where theta is the usual parameterization of solitons in KdV. For the hadrons, Toda and all that, theta is just the momentum of the particles, and then this is density. For the BBS, this is the density of boules, just by the definition of theta. Theta is the soliton length. Okay, and more than that, for all these cases, the effective velocity always satisfies this equation, where phi is just the two-body scattering shift of the asymptotic objects. You just need to do a two-body calculation. Right? You don't need to do anything else. You have your many-body systems. Identify the asymptotic object, do the two-body calculation. You have all the information you need to write the hardware equation. Not to prove it, but at least to write it. Okay? And here, this is, for instance, the KdV soliton shift, and hardware does that, and Toda gas is a two-body, two-particle shift. In the quantum Lieb-Liniger gas, this is the derivative of the log of the two-body scattering phase. And in BBS is this one. So it's always the same equation for all these very different systems. Okay. So yeah. So this is the GG equation in general. Now some comments about that. I mean, it is in general hard to define this object that calculates the number of solitons at a given point in a complicated configuration. It's possible in the BBS and in hard rods, but in general this is harder. Okay, and typically what we have are not we have conserved densities and currents that are just corresponding to integration with a theta of some power of theta. So for instance, the energy is a theta square, the momentum square, and the higher conservation laws in Lieb-Liniger model are the powers of momenta. So we typically have less. Nevertheless, the whole structure is still holds. And you can, in principle, at least in some algorithmic way, define this q theta by taking your configuration, whatever it is in your many-body system, extracting it, some configuration around x, plus minus epsilon, extracting this from the whole system, putting it in the vacuum, so let's say adding trailing zeros in BBS, and then expanding it and seeing what are the asymptotic objects that you get, and that's your density, q theta, d theta. So it's, you can do that in principle even on a computer, right? So you can reconstruct this thing, okay? And that's the thing that will satisfy this q theta is this rho, satisfy the GG equation, okay? So just from a bit of history, so the current, so this whole description of hydrodynamics that I'm giving you actually was quite well understood by many people. For some time, people knew that you just have to calculate the densities and the currents and write down the continuity equation. But people didn't know really how to calculate the currents in integrable system. This J, this was not really known actually. And so this is the thing that we calculated in the Lieb-Liniger model by using TBA crossing symmetry of QFT and some non-relativistic limit. This current was then evaluated in different ways in different model QFT quantum chains by different techniques, more and more rigorous techniques. So now it's very well understood that this is the right expression for the currents, for instance, in integrable quantum spin chains. It's quite very strong mathematics for that. Okay. And the GEG equations, well, so this was written in the hard rod gas quite some time ago. And then in the early 2000s, in the KdV soliton gas, this was written, in fact, was derived using inverse scattering techniques. And then quantum systems, so we proposed that, and then we proposed to hold more generally in every many-body integrable system. So I should also point out that, in fact, in all these derivations, and even in the actual proofs, nowhere was the collision rate ansatz. What was it? So this type of collision rate ansatz. nowhere is this used. Without the derivation, use different technique to derive average values of currents in the GHD equation. And then the collision rate on that is observed a posteriori, which is an interesting fact. So of course, the collision rate on that is a bit hand wavy in quantum system, but nevertheless holds a posteriori. You can see that a posteriori. Okay, so this is the generalized hydrodynamics. Okay. So now one can go further. So this is the GHD equation. Of course, one can, well, so not necessarily of course, but turns out that one can diagonalize it. We've seen it in the talk this morning. So one can find the Riemann invariant or normal modes. Okay? It's a general fact in GHD. Turns out if you define n by rho over 1 plus integration phi rho, that the equation simplifies and the VF gets outside of the derivative. So it looks like it's in a diagonal form. That tells us, in fact, that the VF, by the theory of hydrodynamics, that the VFs are nothing else but the spectrum of this A matrix in hydrodynamics. So here you have the spectrum of velocities. So in GHD, if you do a small perturbation somewhere, what you find are waves, well, a continuum of waves at different velocities determined by these VFs. You can also put external forces, because now we see that as a hydrodynamic equation, so we can do more. So you can put external forces. There was a question asked about that. So there are general formula for an effective acceleration, which is in principle valid again in every many-body integrable system. So if you know the scattering phase, the asymptotic objects, you put that in it and you have the formula. And there's also a way of calculating diffusion. Diffusion is a second derivative term in the hydro equation, a correction to the Euler scale, diffusive scale. This is like a Navier-Stokes kind of a viscosity term, if you wish. Okay? If you specialize that to non-integrable system, it becomes a Navier-Stokes equation. But in general, there's some diffusion operator that one can also write explicitly, although it's rather complicated. But if you know all the properties of your many-body system, you put that in it, and then you have the equation. Okay? And what it corresponds to physically, well, it's kind of a, you know, the little wiggle around the main effective velocity. So there's some kind of Brownian motion around effective velocities. That's what this should correspond to. But in any case, it doesn't have to be interpreted that way. This has been derived by using Kubo formula for diffusion operator, calculating explicitly current integration using integrability, and you get an exact formula for the diffusion matrix, which in principle should be valid both in quantum and classical systems, by the way. So this was proven actually for the hard rods early on by both Tegini and Suhoff. Okay, so now there's something missing. I don't know actually how much time do I have? 10 minutes. 10 minutes, okay. So this was the hydrodynamics. I talked at the beginning about the thermodynamics in fluctuation. So one should go further, right, and calculate the thermodynamics. So how do we calculate the thermodynamics? There's a lot. So what we have to calculate is the free energy. In fact, there are two things that really one should calculate: is the free energy and the so-called free energy flux. So the free energy is the log of the partition function. So again, I write this way. So essentially, that integral should go like exponential minus LF. Okay? And the free energy is a good thing to evaluate, because then you can calculate not just the densities, but also their correlation. If you take two derivatives of the free energy, you get the 2-point function of conserved densities, QQ integrated over X. That's a non-trivial quantity. That's a correlation function. Okay? And it turns out by general principles of statistical mechanics that there always exists a function called energy flux, free energy flux, G, of the betas that generates the current. So this is a general theorem. So there is the G such that the currents are dG dBi, very much like Q. These F and G are kind of the basic things that you would have to calculate. G is simply related to the entropy current. Okay, anyway. So, and you can calculate from the G, then if you take two derivatives, you calculate the 2-point function density current, for instance. Okay, so these are correlation functions. Of course, you can get higher and higher correlation functions. And so that gives you more information than just the hydrodynamics. It's about the initial state. Okay. Now, so how do we calculate this partition function, this free energy? Well, here again, so we have there are different ways, but one powerful way is to go to the asymptotic space. Okay? So now we have particles. So suppose we have particles X and P's. So we look at the asymptotic region, and when we see asymptotic particles coming out, and we see asymptotic momenta and displacements. Okay? Now, this passage from XP to the asymptotic data is a canonical transformation in Hamiltonian system, and the asymptotic data satisfies simple equation. The YNs are like the angle variables, and the theta is the action variables. Okay, so in any many-body system, this is what's happening. It's also true in the BBS, where your thetas now are the soliton lengths, and the Ys are their positions. Essentially, the shift if you extrapolate the trajectories. Right? And then, okay, what you want to calculate is your partition function of free energy by writing everything in terms of some empirical density for these asymptotic momenta. Okay, so how does that work? So you write your initial partition function, okay, and you measure in terms of asymptotic data, Ey d theta. Okay, so then in terms of asymptotic data, the GGE itself becomes very simple. It just depends on the thetas. Right? So it just depends on theta 1, theta 2, theta 3. This is the empirical density there. So it's a very simple thing. Does not depend on the Ys at all. Right? So that simplifies a lot. So the Gibbs measure does not depends on these angle variables. But importantly, there is a constraint on the volume where your system should lie. And so essentially, you have to integrate over the Y, the shifts, the impact factors, just on the right space of Ys, so that at time 0, so on the right space of asymptotic Ys, so at time 0, you end up with a many-body system supported on a volume L. And that is rather non-trivial. So this is a passage from the asymptotic position to the real position, and that's non-trivial. And this is what makes the calculation of this thermodynamics more difficult, right? Okay. Now, in the large volume limit, this empirical density becomes a continuous function of theta. This is this rho p of theta. Okay. So, okay, now to get the free energy, what we do something that has been very similar to what's been explained in the previous talks. We consider some kind of a change of metric or a scattering map on the coordinates. Okay? And then the idea is relatively simple. So you have your coordinate, your x space where the particles lie. And if you look at the particle there, so xn is there, you want to see where it goes far in the in region, so asymptotic space. So you propagate it backward, or you can do forward. And every time you hit the particle, there's a jump. Right? And so as you go from x to the shift of the trajectory y, there's some accumulated jumps. And one way of writing this set of accumulated jump is this equation. So the yn, where this particle, the nth particle is asymptotically, is xn plus a sum of all the jumps that are accumulated as you go backward to the asymptotic space. In fact, that formula is a symmetrization. Let's say it takes into account in and out space, but it doesn't matter too much. Okay. So essentially, you map these x's to these y by accumulating the jumps. And when you do that, you realize that the volume that you have in your y space, like the dy, is related to the volume in x space by a certain function, which is something that we have referred to as the space density, the density of free space in your actual real space. Well, in the hard rod model, it's just the space in between the rods. This is where the rods can be. But in general, this can be defined in that way. There's one, say, the normal space density, plus the added space that occurs from the scattering. So it's like the particle theta, so this is dy of theta, okay? The particle theta sees a different metric, a different space. It's less or more space. For the hard rod, phi is negative, so it sees less, also for the busbar system. But for Lieb-Liniger, it sees more. Or for the hard rods with negative rod scale I was talking about, then we see more. So you have more or less space, okay? So this is just coming from the scattering, but now implementing this change of space from x and y, you can work out exactly that constraints on the x. So the x's must lie there, hence the y must lie there. But where there? Well, there depending on the thetas. Do a large deviation analysis and you get the usual TBA equation that have been written some time ago, Araday by Frank and Yang, but in a more general form. So sorry, this is a bit of a complicated formula. You don't need to know so much about it. The only thing that is important is that you can calculate the free energy by integrating a certain function of something called the pseudo energy. And the function, so this is an additional data, the function you integrate here depends on the model. So there's a function in this thing that encodes the statistics of the asymptotic particles. You have an additional data for fully specifying the models. For instance, in the hydrodynamics, Toda, and KDV, this is just the usual Maxwell-Boltzmann statistics. In the Lieb-Liniger gas is the Fermi-Dirac statistics, and BBS also is the Fermi-Dirac statistics, as if they were fermion for some reason. It's a counting thing. So in BBS, two solitons going to be on top of each other. Actually, I didn't fully understand why, but this comes out from the calculation. Okay? There's always a statistics function depending on the model. It can be more complicated. You can have Anion or whatever, right? But it's a statistics function. And our integral, many-body integral model apparently do satisfy, are recovered by this form of the free energy. Right? So from this you can evaluate the hydrodynamic matrices, some complicated equation, some integral equation that needs to be satisfied, solved and all that. But for all correlation functions, essentially you have the explicit expression. Even for correlation function at large space-time distances in GGEs, there are some asymptotics that you can calculate by using principle of hydrodynamic projection. So you can calculate a lot of things at large scales in space-time by using these things. You can even calculate this full counting statistics that was talked about in the morning by using these C's and A matrices, by using hydrodynamic matrices. So there's a whole hydrodynamic theory that gives you exact expression for integrated current and correlation functions just in terms of these A and C matrices, and you know them in GHG, so you have explicit expression for this. So in particular, this can be written quite simply. Okay. So, but I want to go into too much of the details of this because the expressions becomes quite complicated. They simplify a lot in the BBS, as we've seen in the morning, which is very nice. And then they have all kinds of special properties, which are nice. But in principle, all these things can be calculated in the hydrods, in the Toda model, in the Lieb-Liniger. You're just putting the information in the formulas, kind of a black box type of thing. Okay. Now, I want to say something about this change of metric. This is very interesting, was talked about in the morning. And it can be used to derive the GHG equation. In fact, that's the way that people have derived GHG equation in hydrods and BBS, okay? By controlling this change of metric at the macroscopic level. Okay, so it's very interesting. So what it says is essentially, it says that you can go from the x, the position of your particles, your quasi-particles, the solitons in the real space, which is complicated, to the asymptotic position by a certain map, and the asymptotic positions evolve trivially. So what you write, so if I say that my asymptotic position evolves trivially, and I write my change of coordinate, I get some kind of real space-time Bethe equation. So I have some y-ends that determine the initial values of these x's, and I put the time in it, and that determines how these x's evolve in time. I should take that as a fundamental macroscopic model for positions xn. Okay, this is the time evolution equation. So it's an approximate representation of what's happening. But if you define cleverly the positions of your solitons in your many-body system, that times 0, say, then this is exact. It's like under the correct clever definition, this is an exact equation, right? Macroscopic equation. The whole point is indeed to find the correct definition of your quasi-particles so that this is exact. And it's not hard to see that if you define your density of particles at x and theta like this and use that to get the GHG equation. So this and that implies the GHG. Very simple, okay? So that's a way of proving GHG equation. Now you can write that in the continuum version. Turns out that the relation is y equals integration of the space density of x, well, dz here. So dy is rho s dx, okay? And if you impose that the density of particles in the y coordinate, I call this rho n, because of normal mole density, satisfies the free particle Liouville equation, which it does, then we had shown some time ago that doing that change of coordinate, you get the GHG equations. That's also how people have kind of, it's a generalization of the hydrods and BBS, which works quite generally. Okay. And this is not just a little observation, it's actually an interesting observation that allows you to solve the GHG equation by quadrature, if you wish. Okay. So you can write, you don't have, okay, the GHG equation in terms of normal mode is like that, right? This is hard, this can be hard to solve. It's a dt dx, and you don't solve that numerically on the computer. You can rewrite that as an integral equation. So you write your normal mode, you say this is, since it's normal mode, it follows the characteristic equation. So you write this as theta u0. So essentially, the position x becomes the position u at time 0. Okay? And what is this u? Well, it satisfies this non-trivial, non-linear integral equation where you integrate from some point far in the past where nothing moves the space density, and at time 0 you add the effective velocity times t, and that's the same thing as integrating the space density at time t. And that's actually a way of solving the GHG equation by recursion, which is numerically rather quick and very good. So this is kind of a solution to the GHG equation. So GHG equation has integrability structure somehow, and this is a solution by quadrature of the GHG equation itself. Okay. And finally, about this change of metric, so we were saying, so in the trick would be to say that this equation is exact macroscopically, and then we have, that's it, we have shown GHG equation if we can find the right definition of this xn and all that. So this is essentially what's done in the hard rods and DBS. Okay. But it actually can be done, so we think, so we're working on that, in the Lieb-Liniger model as well. So one way to do that, you take the quantum Lieb-Liniger model, it's quantum gas particles, Bethe ansatz solvable. Okay. So you write the Bethe ansatz eigenfunction. This is the Bethe ansatz eigenfunction. Okay. So there's a sum over permutation because it's a bosonic system, not too much. Okay. There's a e to the I theta x, so these are the asymptotic momenta. And then there's some kind of phase there because the Bethe ansatz wave function has a phase shifts whenever particles. So this is an explicit form. I mean, it's written in books for a long time ago. And this Bethe ansatz wave function evolves trivially because that's the whole point. It's an eigenfunction of the Hamiltonian. And yes, okay. And then what you could do is some kind of quantum modulation. So modulate this Bethe ansatz wave function by putting in front of that a function of the x's that varies slowly in space, slowly varying. In fact, the way that you can put it, instead of function of the x's, you put a function of the y's of x's where the y's solve this equation. Okay? So you do this transformation of value. Explicitly, the y's are explicitly defined like that, macroscopically, right? And it turns out that if you put this function minus theta t here, then that solves the Schrödinger equation for the Lieb-Liniger model. Okay? So the Schrödinger equation gives you the trivial evolution for the y coordinates defined in that way in the slowly modulated wave function case. So this is kind of a derivation of the GHG equation for slowly modulated Lieb-Liniger wave function. Okay? It's not still in preparation. Similar ideas as for UBS and hard rods, but here for quantum slowly modulated thing. Slowly modulated is not very hard to see because when you slowly modulate, essentially you do wave packets. And wave packets interact with each other in a nice way. And the calculation essentially does that. Okay. That's all I wanted to say. So there's a lot of things we can do with GHD. It applies to many models. That was kind of the point of my talk here, that it applies to many models. These are the models where it's being worked out. It has integrability structure. There's even some MATLAB that's been written to solve the equations. You can calculate correlation function, full quantity statistics. And what needs to be done still, well, deriving it properly and evaluating higher order hydrodynamics like dispersion. One can in principle do that. Integrability breaking, right? You add some term that break integrability a little bit. How does this kind of collapse to standard hydrodynamics? Maybe there's turbulence, and maybe one can show rigorously some of the general equations that are there, and not only derive GHD, but show hydrodynamic projection principles and other things. And yeah, so thank you for your attention.
Other questions or a comment?
So you mentioned that the free energy is somehow calculated for PBS and explicitly and match some other models. And so do you have any idea what is the reason for this free energy?
Why it always has the same shape, you mean?
Yeah.
So it's not completely obvious, but yeah, my understanding is that it is the calculation. It is based on the scattering theory, essentially. So it is based on the scattering map. So the idea is that that scattering map that you discussed in your talk, right, and discussed here, always exists in all these factorized scattering integral model. And that's what you use to calculate the free energy. And if it has a structure, then the free energy has this the same structure for every model. What is non-trivial in there is that there's a statistics function, statistical function, Yeah, so I mean, yeah, why? I mean, it's not completely clear to me. You know, what will be the statistical factor?
So
BBS
you only
is
see
numerical. Yeah, just not
two
completely.
different types of, or just you show two types, but there are others.
There are, yeah,
there
there are more types. Yes,
more types.
in principle, you can. There's the Bose-Einstein, so the bosonic factor, so that appears in certain models. In fact, you can write the Lieb-Liniger model in terms of the bosonic instead of fermionic. The Maxwell-Boltzmann. There's also the what is it, Rayleigh genes or whatever, the kind of the wave dispersion relation. So instead of exponential minus epsilon is log of epsilon. That also appears for instance, in the sine Gordon model, you have this continuous wave, or even KdV. You have this not just the soliton, but the waves, the continuous part of the spectrum. So this has a different f of epsilon.
Okay.
And supposedly you can figure out models where there will be something anionic. I don't know. This hasn't been worked out yet.
Okay. And one more question is, so you wrote Qi as this kind of a sum of infinite, but not in integral form. So is there any intuitive reason? So
sorry,
Q is
do you remember which page?
the very beginning. So you always use the Qi.
Yeah.
As and the
Qi yeah.
So why it's countable infinite?
Yeah. So I mean, like here, for instance.
Yeah,
right?
for instance.
This type of stuff. Yeah.
Yeah.
So yeah, I mean, okay. So if you have finite number of particles, that's fine. All that. If you have infinite number of particles, then this can blow up now. But this is kind of the empirical density, if you wish. You sum of all n, and then eventually these in GGs now that should now become a nice continuous function of P and X. Okay. Is this so sum of all particles? So I don't know. It's just a way of defining it. It's not necessarily actually the best way. In fact, it's not. So if particularly if you want to calculate correlation function, that's probably not the best way. Probably the best way would be to do a small average over a fluid cell. So not just sum of delta function, but average the number of particles within a cell, of certain length. That is much smaller than the variation length, but bigger the microscopic length. And now you're going to have something nice and smooth. So that might be a better way.
Okay. So your image is particles, so you use countable infinite.
Exactly. Yeah.
Okay, I see. Thank you.
Are there more questions or comments? So I have a curiosity. So in this list of models that you have,
yes.
so if I understand correctly, the added value of having a less rigorous way to derive the dynamics is that you can treat more.
For sure. Yeah.
And is there an intuition of the fact that the KdV and the Toda have this logarithm as a scattering?
Well, yes. I mean, this is actually a good question. I don't know the full intuition. I mean, of course, the calculation gives that.
Yes.
And it turns out that in many classical models, you have this logarithmic two-body scattering phenomenon. Classical particle model. Or even in the classical sine Gordon, you have this logarithmic. So I don't really know why, actually. It's a good question.
Okay.
It is interesting. So in the Toda model, so this logarithmic form has some kind of scaling invariance. If you scale the momentum, you add the number. Okay, and this is something that seems to have to do with the lack of well, in the quantum case, the interaction strength is important, but in classical case, you can usually take it out. I mean, you can rescale your variable, and then interaction strength can go away. Like in KdV, you don't have any parameter in your equation. It's just it's a parameterless equation under the right scaling. So there's some kind of scaling invariance in classical system. Like h bar is 0, so you can go very small in your phase space. So this is some kind of scaling invariance, and it looks like that's why you have this log. So it's like a 0 phase space type of thing.
Okay, thank you. So let's see from online. I think there is no one. Okay, let's thank Benjamin again.